So we're looking at our pre-calc notes for 10-4 mathematical induction. So math induction is a way to prove something. It's a very interesting way to prove things. The way we show it is we show that it's true when your n equals 1. Then we assume it's true for k, and then we prove it's true for the term after that. So it's kind of a different way to prove something because you're basically proving it by saying it's true for this because it's true for all the cases that happened before. So it's kind of an interesting way to prove. So things to keep in mind with math induction is that our format matters. You have to follow the format. So follow format. Let's see, I need to lock this. Follow format. So we are doing these 3 steps every single time. We're going to work on one side. So just like we did with trig identities, we're not going to be like adding 6 on both sides or multiplying both sides by 3. We're just working on one side. And what else did I want to add on that? I think that was really it. Basically just that you're working on one side, this idea that you can't cross your equal sign. So maybe we should write that also. Don't cross equal sign. So those are the 3 things to remember for formatting. So what I see here is I see an example where we have a first term and a second term and a third term. And if we add that all the way up to our nth term, which is n squared, then this is our answer. So our first step, and I'm actually numbering it 1, just like I wrote on this list up here for steps, is to show that this is true for n equals 1. So that means I am showing that when I have my first term is 1 squared. This is my a sub 1 where my n equals 1. That means I could put n equals 1 in here, and that would be true. And we are proving that something is true. So these will work every single time. So this isn't like, does it work, yes or no? It works. Go ahead and prove it to me. So my first term was the 1 squared, and then I put 1 in for all the n's here, and I'm just showing that this is going to work out. Let's see, 2 times 1 is 2, plus 1 is 3. So I end up with 1 equals 6 over 6. So 1 equals 1, and that is true. So the next thing I want to do is I want to assume true for n equals k. So that means I'm going to rewrite this whole thing here, and instead of 1 squared plus 2 squared plus 3 squared, and then dot, 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 instead of plus n squared, I'm going to say k squared. And this is a necessary step. I do need to have this written out with k. I know it seems like it's just like what we did up above, but it's just that one of those finer points in math. So now we're going to assume that this one's true. So we're going to use that to prove that it works for the term after it. So after k would be k plus 1. So now we're going to prove true. Let's go ahead and move this up. So 3 is going to be, and I don't mean to have a line here. I was just trying to move my tablet here. So 3 is we're going to prove true for n equals k plus 1. So the way I'm going to start that out is I'm going to write everything I have up above, 1 squared plus 2 squared plus 3 squared plus dot, dot, dot plus k squared. And then after, oops, forgot my dots. And then after k squared would be the k plus 1 term. And so that's going to have to be k plus 1 in parentheses squared. And then because I now have a k plus 1 on my ending, my n equals k plus 1, I'm going to take this formula over here and I'm going to put k plus 1 in for all the n's. So that's going to be, instead of just n, I'll have a k plus 1, and I do have to have parentheses. Instead of n plus 1, next here would be n plus 1. But I'm going to write k plus 1 where that n is, and then there's a plus 1 after it. And then 2n plus 1 is going to be 2 times the k plus 1 plus 1. I'm really kind of having to squeeze things in. So we are allowed to go ahead and simplify a little bit on the right. So I am going to do that. So by simplifying on the right, I mean that where it says k plus 1 plus 1, we're just going to write k plus 2. And then I want to think about what's going on in the parentheses here. This would be a 2k plus 2 plus another 1. This is 2k plus 3. So now that I have that all cleaned up, I'm really going to work on the left. So what proof by induction says we can do? And I got to scroll a little tiny bit here. So what proof by induction says we can do is I know that all of this stuff here is equal to that. So down in the problem I'm working now, I'm going to take all of this 1 squared plus 2 squared plus 3 squared all up through k squared. And because I know that this is true, because I've assumed it's true in step 2, I'm going to replace this with k times k plus 1 times 2k plus 1 all over 6. And then I still have, after that, the quantity k plus 1 squared. So now in order to prove this, all I'm basically doing now is I'm simplifying on that left-hand side. So this is where it's kind of like a trig identity, except we're using algebra. We're not working with sine and cosine. We're just trying to show that algebraically the left side is going to equal the right side. And we're going to leave the right-hand side the way it is. So because I'm not changing the right-hand side at this point, I'm going to use the notation that we used in our trig identity chapter. I could leave it just like a blank equal sign, but we're going to write right-hand side there just to kind of keep things lined up. And on the left, if I have this over 1 right now, I'm going to have to get a common denominator. So I'm going to write k times k plus 1 times 2k plus 1 all over 6 plus, and then here I have 6 times the quantity k plus 1 squared all over 6. So I'm multiplying by 6 over 6. And let's go ahead and do another step now. I'm trying to give myself plenty of space to work. I'm going to add these together. It's all going to be over 6. And I'm not sure about having that k plus 1 quantity squared. I am going to just write it twice instead. So I could totally do this step right now just looking at it, but I think if I show a tiny bit of work in here, it's going to make more sense to you. So it would be really tempting on the left-hand side now to go through and multiply all this stuff out and then refactor it and see if I could get the right-hand side. But because I'm going to have a k times a k times a k, because we're going to have k cubed, the factoring could be really, really difficult. So instead, what I'm going to do is I'm going to look at how there's a k plus 1 here and there's a k plus 1 here. And I'm going to use factor by grouping. And so I'm going to take those two and I'm basically going to factor them out. It's not really 2, right? They both have it. So it makes a factor of k plus 1 in front of everything. So what I would have left is my k and my 2k plus 1. And then a plus. And then over here I would have left the 6 and the k plus 1. And then, of course, this is all over 6. So usually this is where people need to kind of pause the video and think about that. But because they both had this factor in common, I was able to put it out in front and then look at what's left. So when I looked at the structure of this, I really saw the plus sign with 2 different big groups of things. And those groups both had the k plus 1 in common. And that's why I highlighted it. So if this was my own work, obviously on my own paper, I wouldn't be highlighting it. But I do think it kind of helps to look at what's going on here. So now what I'm going to do is I'm going to keep the k plus 1. And I am actually going to go through and simplify inside. So I am going to multiply it all out and then hopefully refactor it. And now when I multiply it out, I'm not going to have a k cubed anymore. So my factoring is going to be pretty easy. So it would have been possible to have multiplied the whole thing to start with and still get the right answer. But if you don't notice factor by grouping on these, it's going to be really difficult. So now I've got to factor the 2k squared plus 7k plus 6. And the cool part about this is I know what it's supposed to equal, right? I have this thing up here that it's supposed to equal from the very beginning. So a lot of times what I'll do is I'll even just like look at how it's factored and say, hey, does that actually match with what I have down here? And if those are the same, and it's a lot easier sometimes to actually multiply it out and check it, k times 2k would give me the 2k squared. This would give me a 3k and a 4k. That makes 7. A lot of times it's almost going to be easier to just kind of do that answer check and work backwards than to actually factor it out. So looking at that, I'm really confident now that the factoring is the same. So I am going to have proved it. I just have to write k plus 1, parentheses, times, oops, my thing's not wanting to lock anymore because I'm on the next page, 2k plus 2, and this is a k plus 3. And I don't know if I have them in the right order or not, so I just want to check that really quick. I don't have them in the right order. I want them to look exactly the same on both sides, so I'm actually going to flip the order on these. K plus 2, 2k plus 3, all over the 6. So this is equal on both sides. I really should rewrite it one more time, but I'm out of space as it is. One thing that we write sometimes, especially in geometric proofs after we've proved everything, is they abbreviate that proof with Latin. I don't remember what the Latin stands for. You could totally Google it and look it up. But QED just basically means like I've proved what I wanted to prove. And it is a Latin thing that we do a lot of times in geometric proofs, but it's totally appropriate here. Sometimes I just goof around and put a smiley face at the end because I'm glad I'm done. I've seen students do check marks. We don't really care. You don't even have to write anything. But basically, we have the left and the right are in complete agreement. They're exactly the same. And so we're done. So this first example was really about as difficult as they get. We had fractions. We had a bunch of kind of slick factoring. We had to use the factor by grouping. The second example we're going to look at is going to be a little more straightforward because we don't have any fractions. The exponent ones are going to be tricky as well. So there's a lot of algebra, and I really like that part about our math induction proofs is that you're really having to go back and kind of refresh algebra. So prove by induction means we're going to just do our same steps again. So the first step is always that we're going to show true, and I always write this down for n equals 1. So that means my first term. So my first term, my a sub 1 is 2. And then if I'm looking at my first term, that means my n equals 1. So I'm going to write down that 2 equals, and then I'm putting a 1 in for my n's. And this will always be true. If this is not true, you have screwed something up and you need to double check it, get some help. And so I show 2 equals 2. So it's really confusing, I know, that this first term is 2, but I'm not putting 2 in for n's. Because it is a sub 1, I am putting 1 in for n. So I'm using my first term, and for my first term, my n equals 1. So the next thing I want to do is I want to assume true for n equals k. So that means I'm going to rewrite the entire thing and put a k in instead. And this is what we do every single time. So first we show n equals 1, then we do this n equals k step. If you do not follow the format, I think the best you can hope for is half credit. So there's a really specific way that proof by induction needs to be done. And it was not my decision. I am not the one that came up with this. I am just the one following the pattern. So proofs are a very specific thing that we do. So all I did now is I rewrote everything, and instead of the n, I have the k. So that's always our second step. So step 3 is where we have to do all of our algebra. So for step 3, we are going to prove true when n equals k plus 1. So k plus 1 would be the term after 2k. So I am going to go ahead and I'm going to move this up a little bit so I have space. And I'm going to write 2 plus 4 plus 6 plus etc., plus 2k plus, and then the next term after that, instead of a k, I'm going to have a k plus 1. And I have purposely made a mistake right now that I'm hoping you can spot. So if I have 2 times all of k, over here I should have 2 times parentheses k plus 1. So you're going to have to be really careful. There's going to be times when you're going to have to add your own parentheses, and you're really going to have to watch for that. So now on the right-hand side, instead of this k, I would have a k plus 1. And instead of this k, I would have a k plus 1. So I'm going to have k plus 1 plus 1. So now, just like every other problem that we've done, I know that all of this stuff is the same as I have up here. And I know, according to what I have already assumed, I have said that all that highlighted stuff is equal to k times k plus 1. So now I make that substitution. And you don't have to make a big bracket there. That's something that I'm just doing to show you. It is absolutely not necessary, but I just find it really is helpful to students. And on the right, I just want to simplify and make a k plus 1 times k plus 2. And oh, look at that. What I am noticing on our problem is that they both have this factor of k plus 1. I can do factor by grouping and get my answer right away. So when I factor out that k plus 1, and again, like I wouldn't draw these arrows either if this was my own work, it means I'm going to have a factor of k plus 1 times whatever I have left over, which is the k and the plus 2. So my second binomial will be k plus 2. So I could have multiplied that all out and then refactored it, but factor by grouping has saved us some time again. So we are done with this one. Check, it's done. Or you could write, of course, our fancy Latin phrase. You should definitely look that up. I don't remember what it stands for, but I know it's Latin for I've proved it. So the last problem that we're going to work together is going to be a little bit different. And you need to follow the work that we're showing here. So you're going to show work like notes, not Glencoe. So if you go back and you look in your Glencoe textbook, the work is going to be a lot longer. I think it's harder to understand. I really like the way Kelly is actually the one that decided how to show this and how to do this. It's from a different textbook. And I really like, especially after she's gone through some of the other methods with me, I think this one is by far the easiest for you guys to understand. And it really looks like all the other stuff that we've done for this section. So I think it's nice, but it means you can't go back to Glencoe. So you're going to have to look at your notes. You're going to have to get help. So we're going to show the work a certain way. So we're showing it my way. We're not showing it Glencoe's way. So first, we're still going to show true for n equals 1. And this is different. This time we're showing that something is a factor. So these is a factor problems are different. So we're showing 2 is a factor of n squared plus 5n. So I don't have like a bunch of stuff equal. All I have to work with is that n squared plus 5n. So I'm going to make this 1 squared plus 5 times 1. And that's 1 plus 5, which is 6. And then I just want to think, is 2 a factor of that? Yes, 2 is a factor of 6. So a factor means I could take 6 and divide by 2 evenly. It means 2 times something equals 6. So if you think about what it means to factor a quadratic, I factor my quadratic by writing this one as this k plus 1 times k plus 2, right? I multiply two things together. Those are factors. So, and it could be more than 2 factors. A quadratic, I guess not necessarily a quadratic, but a cubic, something else that could have more than 2 factors. But those are factors, things that we multiply together to get something. That was a kind of a sticking point in my class today. So I wanted to make sure that we understood that. So 2 is a factor because 2 can be multiplied by something to get 6, or 6 is divisible by 2. So my next step for this one is always that I want to assume true for n equals k. So the way that looks for this one is that I would just put k's in instead of n and write k squared plus 5k. And I'm just going to assume that 2 is a factor of that. So 2 is a factor of k squared plus 5k. 5k. So again, we showed when n equals 1, we got 6. 2 is a factor of 6. When n equals k, we have k squared plus 5k. So 2 is a factor of k squared plus 5k. So that's what we're assuming. And then our step 3 is we're going to prove that it's true for n equals k plus 1. So that means if I put k plus 1 in for both of those n's, and all of n is squared, so all of k plus 1 is squared, 5 times n, so I have to have 5 times parenthesis k plus 1. So now I need to show that this is a factor of 2, or that 2 is a factor of this, other way around. So my first step is just to expand, right? I'm going to have to do something. So I'm going to go ahead and expand this. So k squared plus 2k plus 1. So remember, your middle term is always doubled. This is a 5k plus 5. And then just like before, I'm trying to get a k squared plus 5k out of this. Because if I have a k squared plus 5k, I know that that is divisible by 2, and then I can look at what's left. So sure enough, here I have a k squared, here I have a 5k. So I'm going to go ahead and write those out in front. And I'm going to separate them off with parentheses. And then I have left a 2k and a 1 and a 5, which is going to be 2k plus 6. So because I have already assumed that 2 is a factor of the k squared plus 5k, I know that 2 is a factor of this. So that part I'm all set on. But in order to show that 2 is a factor of 2k plus 6, I would show that I could write it as 2 times something. So I'm going to factor out the 2, because if I factor out the 2, I am showing that 2 is a factor. So my last step on this one's just about done, is to say that this part right here, oops, gotta get my pen again. I've already assumed that 2 is a factor of that up above. So I already said that 2 is a factor of k squared plus 5k. And now this part, I already know 2 is a factor of because it's being multiplied by 2. So 2 is a factor of 2 times k plus 3. And so we're all set. If 2 is a factor of both of those parts, then 2 is just a factor. So that is it for our proof on this one. So again, these notes are a lot different than Glencoe, but I think they're going to be easier to follow. But that does mean that we do not have our book to help us. So if you need any help in class, please do not hesitate to ask. We've got work that we can show you if you want to see how our notebooks look and how we've solved problems. So that is it for our 10-4 notes.